Hello, IB Math course students. Let's get back to Unit 7 measurement. Today's lesson is about surface area of curved surfaces. So we're going to apply what we did last time, but now we're going to look at curved areas. Now, we want to be able to explain why in compound solids you cannot simply add together formulas for surface area as you see them presented below. Now, curved surfaces can be used to model many real-world shapes. You want to think about stuff like ice cream cones. Well, that's made up of a hemisphere on top for the ice cream and then a cone at the bottom. You're putting together those two shapes. You also have treasure boxes. You have like a rectangular prism and then a half of a cylinder to represent the top of it. Silos on a farmland. We've got a cylinder that reaches up very tall, with the very top of it being a dome or a hemisphere up at the top. Now, three basic shapes that you guys have covered since geometry will combine to make a lot of real-world shapes. So we want to be comfortable with them and working with all the different components. So that way we can build lots of different kinds of solids. Let's start off with the cylinder. So remember that with a cylinder, you're going to be made up of the face. It's kind of like the face of a can of tomatoes or something like that. And that is your curved surface. And that is going to be utilizing this piece of this formula, 2 pi rh. Okay, and where that comes from is if you unwrapped it, you would have the height as one dimension and then the entire circumference as the other. That's where the 2 pi r comes from. Now, the other part we would see would be your cylinder tops and bottoms, which are made up of two circles. Area of a circle is pi r squared. We have two of them, hence we have 2 times the area of a circle, 2 circles. Now, you got to be careful because a lot of times you'll have open-ended open top or open bottom cylinders that are hollow. You just want to be careful of that. You might have to take away one of these pi r squareds or even both of them when you're working through these problems. Next, spheres. Area formula for a sphere is 4 pi r squared to give you this surface area. The origin of this is going to not be really revealed until calculus, which you'll do later on in your math careers, but know that you're going to be needing to find the radius. A lot of times you're given the diameter, or you're not going to be explicitly given the radius, but you should be able to find it in some way. And a lot of times also you're going to be cutting this thing in half. If you cut this in half, maybe you're looking at like a solid bowl, which has a top covering on it. And if you're doing that, you got to be also mindful and aware that, hey, if I am only looking at, say, a hemisphere, but the top of it is solid, then we might need to be adding in that extra circle part of that area too. So just be aware of that. That could exist. The next part that we would want to look at is a cone. Now the cone, we've got our circle base, that's pi r squared. That's pretty straightforward and self-explanatory. But then you also have this slanted part, the curved surface. And the curved surface is made up of your pi rs. Okay? Now that's this part here. Now, unfortunately, it has this new measurement, the slant height, s. We often don't have that slant height. It's not always explicitly given to us. What is often given to us is the vertical distance from the top of the cone all the way down to the base of the circle, and that's known as your height. Well, that's not too big of a deal, because if you know your height and you're also given your radius, which is also very common, then you can recognize that between the height and the radius and s, your slant height, you are going to be given a right triangle here. And if you're given a right triangle and you know 2 of the sides, you should be able to find the third. So this is often going to be found by using the Pythagorean theorem. So what I want you guys to do is take a moment to write these formulas down for yourself, because the more you write them, the more likely you will be to remember and understand them. I'm giving you space here below to do that. Now, at this level, you do need to be comfortable combining and breaking apart these different shapes. Let's see some ways that you can do that through some examples. All right, for our first example, we have a solid hemisphere that is shown here, and we can see pretty clearly that we have a radius equal to 3 centimeters. So what we want to recognize is that we have half of a sphere, so the surface area of half of a sphere is going to be that 4 pi r squared, but then we are also going to cut it in half because it's a hemisphere. Okay, now the other thing you need to also be aware of, though, since it's solid, that does mean that we do have this top part here, and we need to account for that. But again, that's going to be just the area of a circle. And you'll notice that I like to write out these formulas rather than just straight up plug in numbers in. I want to wait, okay? I want to wait till I do that until kind of the very end. Okay, so we've got the curved part, the hemisphere, plus the closed top. And let's go ahead and now plug in our radius plus pi times 3 squared. I'm going to go ahead and evaluate these without a calculator for right now. Well, 4 divided by 2, that's 2. 3 squared is 9. So there we have 2 times 3 squared. That's going to be 18 pi plus pi times 3 squared. That's going to be 9 pi. And that's going to be 27 pi centimeters squared. So this is an exact answer. You'll notice that we have 27 pi. Okay, I haven't multiplied by pi. I've just gone ahead and found the exact answer. Now, on an external exam, this is always going to be preferred to provide this. But a lot of times, if we're dealing with things like measurement or money, we don't care about pi. We want to know, like, how long is that so I can wrap my head around it. So we might want to round it to 3 sig figures. Let's open up Desmos to do that. And we see that it's going to be 84.823. So again, we're rounding these to 3 sig figs generally. That's going to be 84.8 centimeters squared. Again, we are always looking at these things in terms of the unit of measurement we were given. Recognized with area, we should be looking at squared units. So the next one, you want to take a look at this extra note that I've given to you. Most of the time, you are not going to know the specific components of these formula, but you can derive them. For example, right triangles can be found inside of cones, a radius is half diameter, etc., etc. So here you should be able to see that you are given this entire width of a cone. Well, that's a diameter of that circle. You'll also want to notice that you have a hollow top. And with that hollow top, that means you're going to have to take away that top area because it's no longer a surface if it's hollow. So you're only looking at the exterior surface, the outer surface of this shape, but you're going to exclude that top circle. Go ahead and try and do that on your own, and we'll check your work in class. All right, for our next one, you notice we don't have a picture. We want to find the surface area of a cone, however, with a diameter of 3.6 centimeters and a height of 2.4. Now, until you get super comfortable with this, I'm always going to recommend that you underline your given bits of information and draw a picture. And be very careful how you're drawing that picture. Okay, so it's a cone. Doesn't have to be perfect. Try and draw yourself a nice curved bottom there and make your circle. Again, it's not perfect. We are going to assume that this is going to be a right cone, so it's going straight up. And we are given this vertical distance here, the height. That's my height, and we are given a diameter. So let's go ahead and label a couple of these things. Our height, we know that one is 2.4 centimeters, but then the diameter is 3.6, so you got to be really careful with this. The radius is going to be half of that. So there we got radius equals 1.8. We need to find the slant height, though, in order to work for a surface area of a cone. Surface area formula for a cone was pi r s plus pi r squared. So we got to use some Pythagorean theorem to find that's the hypotenuse, the slant height there. And I know that that's going to be the square root of 1.8 squared plus the height 2.4 squared, because I have that triangle between RH and S. Okay. When I punch this into my calculator, I'm going to get that it is actually exactly 9, and that's going to give us the square root of 9 is going to be 3. So we have a slant height of 3 centimeters. So the next step is to plug everything in that we need into our pi rs plus pi r squared formula. Abbreviate this with SA for surface area. So we have pi times my radius, 1.8, times my slant height, 3, plus pi times my radius squared to account for that bottom part. Now let's jump over to Desmos. And there we see the surface area of this cone is going to be 27.1, and we are looking at centimeters, so we are in centimeters squared. Again, that is rounded to 3 significant figures. So let's go ahead and take a couple of extra notes here and take a look at one more example together. It is rare that finding the surface area is all you have to do. So what you need to do is be flexible. We are faced with a lot of word problems depending on the class that you go into next year. Here's one that would be very typical of a math AI style question. Now, a new wharf has 24 cylindrical concrete pylons, each with a diameter of 0.6 meters and a length of 10 meters. The pylons will be coated with salt-resistant material. What we want to do is first find the total surface area of one pylon. Then we are going to recognize what the cost is of coating just one pylon, and then thinking about coating all 24 of these pylons. Let's get to it. I want to first write down the things that I know that are going to be helpful to me. Okay, so I have a diameter of a cylindrical pylon that's 0.6, which tells me that my radius is actually going to be 0.3 meters. And then I have a length or a height of 10 meters. So that's, 10 meters. So that's going to be helpful for me. Now, first things first, we want to find the surface area. Well, again, we have our surface area formula for a pylon, for a cylindrical pylon like this is going to be 2 pi r h plus 2 pi r squared. Plug in the things that we know. We have 2 pi times 0.3 times 10 plus 2 pi times 0.3 squared. We'll go to Desmos to find that value pretty easily. And we'll find our surface area. And we see that's going to be about 19.4 meters squared. But the trick here is remember that when you're doing your further calculations, you do not want to use any of these rounded values. So we'll write down 19.4 meters squared rounded to 3 sig figs, but we're going to put a pin in this value here. Let's go and take a look. For part B, coating the pylons with the material costs $45.50 per meter squared. Well, we know what the meter squareds are. This should be easy enough. This is just a straight multiplication problem. So we have 4550 times 19.4, but we don't want to stop there. Remember, you need to make sure you have all of those digits as much as possible. So we have 19.4150426. Go back to our Desmos, and we'll take that value and multiply. And we see that we get 883.384383. Here's the deal, though. When we're talking about money, we don't want to round to 3 sig figs or anything like that. Money usually is going to go to 2 decimal places. So I think it's generally appropriate for you to be able to do that, especially in like an intermediate answer here. If you're not told to round to a specific value, let's go ahead and give it to the nearest penny, because that's the context that makes sense for us as we're talking about money. So there we have $883.38 for one of these pylons. But now we want to do this to 24 pylons. So we have another round of multiplication to do. We're going to take that value. But again, what we want to do is remember the rounded values. We still don't want to use those quite yet. Since we are rounding to the nearest dollar, it's usually not going to be that big of a deal. But just to be on the safe side, I want to include that little tiny bit there, that 38.54 cents, and include that in my calculation. And when I do this, if I were to go over to Desmos, I would get a value of $21,201.23, and it would continue to go on and on and on. But now we need to round to the nearest dollar. So rounding to the nearest dollar is pretty straightforward for us. That's $21,201. And there we have it, rounded to the nearest dollar. For example, number 5, you guys have a cone that you need to work with. I want you to do that. We'll check your work in class. Okay, so now we get into the real meat of these kinds of questions where we are going to do an algebraic approach. So this is much more of like the typical kind of question you would see that's related to geometry in a math AA style class. So let's think about this. Engineers and other scientists are often going to find algebraic expressions in order to optimize solids and find optimal surface areas or optimal volumes or work behind certain constraints. Sometimes even math students, yeah, you guys have to do this too. And it seems like it's arbitrary, but we're actually really trying to prepare you for something in the future. So let's take a look at an example of like the first steps of these kinds of optimization problems. So we've got a hollow cylinder. Again, that means that we don't have to worry about this top part. It's got a hollow bar and a hollow bottom part too. Okay, but the height is the same as its diameter. In diameter, we know that's 2r, so that means this is 2r. We want to write an expression for the outer surface area of the cylinder in terms of its radius r. So important language bits here to recognize in terms of its radius means r will be in the answer. Now, what is it that we are trying to write an expression for? For the outer surface area of the cylinder. If we're trying to write an expression for the outer surface area, that means that's the thing that's going to be isolated. That's the thing that's going to be by itself in the equation. Okay, so let's go ahead and look at surface area. For a cylinder, we know that that was 2 pi times the radius times the height plus 2 pi r squared. But remember what each different component is here. 2 pi r squared, those are the top and bottom parts, which we know don't exist. We also now know that h was this value here, 2 times its radius or the diameter. Okay, so let's rewrite this, taking out the things we don't need and replacing it all with the things that we know. So we know that the surface area is equal to 2 pi r times the height, which was 2r, or the diameter. Let's go ahead and rewrite that again. Multiplying through, we see that's going to be 4 pi r squared. And that's interesting. Just happens to be chance here that this is the same formula as the surface area of the sphere. Doesn't mean that this is now a sphere. It just happens to be that way for this particular cylinder. But that's the expression for a surface area. Surface area for that area is isolated in terms of r. R is the only variable in that expression. So that's exactly what we wanted to find. Now, with part B, we want to find the height of the cylinder if its surface area is 91.6 meters squared. Well, we know that the height of the cylinder is really just 2 times its radius. And we have an expression for the surface area in 4 pi r squared. And we know that that surface area is 91.6 meters squared. So we set that equal to the expression 4 pi r squared. Now you'll notice that this is one equation with one variable, which means we can go ahead and solve for this very simply. I'm going to divide both sides by 4 pi to get the r squared by itself, and then I'm going to take the square root. So let's do all that in one step. 91.6 divided by 4 pi, and that's going to give us the value for r. Now, we don't have to worry about the plus or minus here because we can't have a negative radius, so that just doesn't exist. So really, we're only looking at the positive square root here. Let's go over to Desmos and punch this in. Now we have an expression for the radius, 2.699869,699, blah, blah, blah. And we can also go ahead and double this. We know we just need to multiply this by 2, so let's go ahead and do that. And we multiply by 2. And there we have our expression, 5.399,739, blah, 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 blah. We can go and round this now to 3 significant figures because this is our final answer. So 5.40 is going to be it. All right, so example number 7, you're going to be working with a cone. I want you to, again, start to be flexible. Notice the things that you need and don't need, and make sure that you are paying attention to the measurements you're given, whether they're the height, the slant height, and use that Pythagorean theorem for example number 7. When you're done, let's move on to example number 8. All right, so last example. Finally, you are often going to need to combine basic solids together to form what we call compound solids. and then you're going to be able to answer a lot of questions regarding these things. So we want to, with this question, it looks like we've got a kind of a silo shape, a cylinder with a hemisphere on top of it, and we want to find the surface area of this solid. So solid, now let's think about what exactly we need. Well, we need a hemisphere, right? We're going to need this dome space right here, but there's not going to be any bottom to it. So it's just going to be the hemisphere. That's one piece we're going to need. And that's going to be half of our surface area. So that's 4 pi r squared divided by 2, and that's going to be 2 pi r squared. Okay, the next part that we need is going to be the curved face, which we know that was 2 pi r times h. Okay, and then our last piece, we do have, since it's solid, we do have a bottom piece here, and that's going to be pi r squared. So there we've got all the 3 pieces that we need, and it's always a good idea for you to go through this exercise and really realize what are the surfaces that I see. Now, let's go ahead and write down the things that we know. Well, each of these is going to have the same radius, and that radius might not seem super obvious right at first, but we do know that the height of the dome is 1.2 meters, but that's the same as the radius. So we know that the radius is 1.2 meters, and that's also going to be the same thing as the radius of the cylinder. So we've got 2 pieces of information there, really from 1. Now we also have a height. That's 2.8 meters. And if we look at all the things that we need, every one of those has either an R or an H. So we're in business. We just need to add all of these things together. So surface area is going to be 2 pi r squared plus 2 pi r h plus pi r squared. I'm going to combine the like terms that I have. So what we need to see, at least with this one, we need to see something to have a pi and an r squared. Well, I do have a pi and an r squared here. So that's 1 pi r squared plus 2 pi r squared. That's going to give me 3 pi r squared. Now, why didn't I add these 2 together? Because I don't have the same r squared term, so we can't work with that. So we're now going to add together 2 pi r h. Okay, this is a skill you want to get in the habit of. Use the algebra terms. It's going to be a lot easier. Now we can plug stuff in. And that's going to be 3 pi times our radius squared plus 2 pi times our radius times our height. There we get our solution. And again, since we did all of this in one step, we don't have to worry about any of the intermediate rounding. That's another reason why don't plug in your numbers into your equations until you're ready to go to your calculator. Just do it all in one step. And there we can see, now we can round this to 3 significant figures or to 1 decimal place, and that's 34.7. Let's go back and check our units. We do want it to go to 1 decimal place, and that was going to be 34.7. This was in meters, so that's going to be meters squared. And there we have it. There's our surface area. All right, so with the cone, should be fairly straightforward. Combine those different shapes, see which pieces of the formulas you need to add together, and you're good to go. Thanks very much for watching. I will see you next time.